Okay. Next, interference by thin films. Right. This is a thin film, as you can see. There's a very thin film of material, very thin, right? Few wavelengths thick. Light reflects off the bottom and top layer, causing interference. Right. When you look at a soap bubble, right? When you blow bubbles, it has that kind of rainbow effect on the bubble as you look at it as it floats through the air. Or an oil slick, right? Sometimes if there's oil on the surface and a puddle comes on the road and there's a little oil on top of the puddle, you can kind of see that rainbow effect on the puddle because of the oil on top of it. You get that kind of thing. That's called Newton's rings. Those things are called Newton's rings. All right, and if you can imagine, right, and I'll show this in more detail on the next slide, as the light goes down and hits point A, some of the light reflects back to your eye, and some of the light passes and refracts as it goes through the oil, and it reflects off the bottom of the oil, that where the oil and water meet. It then reflects back and then refracts out of the oil and into the air and into your eye. So if that oil is so thin that it's a wavelength, let's just make it one wavelength thick, when the wavelength goes down through the oil and then reflects back from point B to point C, it's in phase as it refracts out of the water because it's a full wave has gone down and another full wave has come back up. They are now in phase. A and C are in phase with each other, right? So that wavelength you can see through your eye or in your eye. You can see that color. And if you could imagine, if we could move the ray, the incident ray, say closer at a larger angle of incidence, and then the reflected ray at a larger angle of incidence, your eye is more to the right in our picture. As it passes through the oil, it's going to have to pass a larger distance than a single wavelength because of the angle it's going. So then you'd have different wavelengths refracting out of the oil, and you get different colors. That's why you get that rainbow effect. Same with soap bubbles. Depending on the angle of incidence, you get different colors. Why is this not going to the next slide? Next slide. There we go. All right, so you can kind of see on the picture on the right what I'm talking about. All right. That distance ABC has to be equal to a wavelength or some number of wavelengths. If it's a half a wavelength, then you get destructive interference and you can get a dark spot. So you don't see the light coming out of it. Right, and you get this rainbow effect in that picture on the right also. Those are called Newton's rings. Just for a little, I don't know, if you ever go in Jeopardy. Okay. I have a demonstration, but I can't show it. I'm sure you won't be able to see it through the picture through the lens, but I can actually, well, I can try, but I don't think you'll be able to see it. I'll try. Let me stop sharing. Okay. This thing here I have is I have two pieces of glass that are squeezed together, right? That's what the wood blocks and the clamps are doing. They're squeezing the glass together. So the separation between the two pieces of glass is as thin as possible. So I don't know if I can do, maybe if I turn it around, because I can get the light to reflect. I have no idea if you can see anything in here or not. Right? But if I can see this reflection off the light, I doubt you can see it, but you can kind of see those colors in here. For those of you who are coming in on Thursday, I'll show it to you again. And you guys can actually see it, what I'm talking about. Okay? All right. We have just a couple more slides and then we'll finish up here. All right, did I do that right? Are you seeing the slideshow again?
Yeah.
Okay, good. All right, just a couple more slides about polarization of light. Okay, whoops, go to the next slide. All right, polarization. So you can see from the top picture there, right? It says in unpolarized light, the wave oscillates in every direction. So a beam of light, right? A ray of light is actually a whole bunch of different waves, and they're going up and down and right and left and at angles and at various angles as they go, as that wave goes up and down at, you know. So there's a whole bunch of waves that are all going in all kinds of different planes as they approach you and they go into your eye. Polarized light, right, causes that light to only pass in one plane. Okay, so we could eliminate all of, like we have the vertical plane, right, that vertical straight up and down arrow, and you can, if you could cancel out all of the other arrows, that would be called polarized light. Okay, and how that happens, here's just using a picture, right? If you imagine here's a board and a rope that we make you wave and make the waves go through on this rope. If the slit in the board is in the same direction as the wave's able to pass through it. But if it's in perpendicular to the wave, when the rope gets to that, it starts hitting the sides of the slit in the board and it's unable to continue on past. So you can see in our little picture here in picture B that the rope on the right side of the board no longer has a wave in it. Okay, and we can do the same thing for light. We can polarize light because unpolarized light again is going in, the waves are in all different planes. But if we take something that has a thin enough little slits in it, we can knock out all of the other ones and only allow essentially the light that's in the planes that are in the same direction as those slits, right, for light. And I'll show you that. I have a way to show you that in a second, right? So here's what I'm talking about, right? Here's our polarizer. You can imagine all of these, this unpolarized light coming in and it hits this polarizer and only the vertical the vertical plane light passes through, right? Which is not 100% true. It's not, actually, I shouldn't even say that. It's not, this is a very simplified version of that, of what I'm talking about, right? And if you can imagine that this polarized light now comes and hits another polarizer that they're calling the analyzer, that is now the slits are perpendicular to the polarized light. It doesn't let any light pass through, right? In reality, what happens is the polarized light that's perpendicular to the polarizers does get blocked, but all those ones that are off at angles, think about vectors, the component of the vector that is parallel to the polarizer passes, but the component of the vector that is perpendicular to the polarizer gets blocked. So the intensity of light of the other planes is less, is reduced as you go from the vertical plane wave to the horizontal plane wave. Right? Does that make sense to everyone? The way I'm explaining it? I'm hoping you're visualizing what I'm talking about. Okay, so we have one last slide with polarization. All right, so that's how we can polarize things using the polarizers. But in nature, light kind of gets polarized itself when it reflects off of flat surfaces and shiny surfaces, glass, water, that kind of thing. Right, so you can see in our picture down here, right, the unpolarized sunlight hits the water, and generally you can see it's represented by the size of the arrows there. The light that is parallel to the surface gets reflected fully, but the light that is perpendicular to the surface gets reflected at a much smaller amount, right? So that causes a glare. You guys drive, I'm assuming you're seniors with the exception of Katie, so you probably all drive. If you ever see like the light reflecting off the car in front of you and it's real, there's a bad glare, it's because the glare is that polarized light. And we can then, right, if you ever buy sunglasses, it's a little more expensive, but if you get polarized sunglasses essentially the glass surface is one of these polarizers, and it only allows, it filters out a lot of the light and it filters out the glare by using these polarizers here, right? So this glare gets eliminated and only the horizontal arrow here in our picture off the water gets blocked by the polarizer, and it only allows the vertical to come through, and it eliminates that glare. Okay, and I have a demonstration for that one that you can actually see. Okay. All right, so let me break out the demonstration for that one. All right, so here is right, this doesn't look this looks old. All right, here we go, right? Here's, this is a polarizing filter. So this is, right, it's dark, it's your sunglasses, right? So it darkens the light. And then here's another one, and if I put them on top of each other, right, you can see it's a little bit darker where they intersect because we have two sunglasses. It's just less light gets through because of the color. But if I move them perpendicular where I want to do it, I change them perpendicular to each other, it really blocks the light, right? It passes through. Now they're in the same plane. The polarizing filters are in the same plane, and now they're perpendicular to each other, and it truly blocks the light a lot more, right? I'm polarizing light and I'm blocking the light because they're perpendicular to each other. Okay, so that should wrap up our notes and our discussion of all of the material from chapter 24. Does anyone have any questions before I turn off the recording on what we covered? Okay, so I'm going to stop the recording. Stop the recording.